Good afternoon, everyone. I'm Murali Ranganathan. I'm part of Meta Connectivity, also the technical lead for the TIP, the importance of Open RAN to operators and vendors. The most recent session, we talked about the RIC and how Nokia, AT&T, and Midea are working on promoting an ecosystem of developers that are going to be building the RIC for us. I would say that this session is the icing on the cake, and we have 3 layers of icing for you to relish today. We're going to address those 3 layers to get folks like you to look into implementing the RIC and the complexity that we need to solve, or the problems that we have to solve in order to be able to implement it. So before I start, 12 years ago or 14 years ago, one of the questions we could have asked the audience is, does anybody have a smartphone? Today, everybody has one, so it's a moot question. But it's important that we understand some of the technology that went into making the smartphone what it is today. So I want to start with that and look at what the smartphone has done to our industry. If you look at any dictionary, there is a word that spells the smartphone. It's a noun. This is a dictionary definition of smartphone that I picked up. Every other dictionary has a slightly different definition. But can the audience tell me what it is that went into the smartphone that made it so successful? Anything that you can think of. One or 2 things? Applications? Yeah. Okay. You guys are thinking just like I am. So the apps, for sure. Camera, somebody said camera. Technology innovations, right? Lots of sensors. Nobody would have thought about putting a 3-axis gyroscope or accelerometers inside a phone, right, back 15 years ago. So a lot of technology innovations went in there, GPS receivers, everything got crammed into that small form factor that made it so successful. It's all in one, right? Camera, it's got the technology for taking pictures. People don't carry keychains anymore. They don't carry cameras anymore. It's all in one. And that's all you carry, right? You have that in your palm wherever you go, and that solves a lot of your problems, a lot of your needs. Now, this is half the problem, or half the solution, if you want to look at it the other way. The other half is the network, right? You need a network to carry all the traffic that these smartphones are generating. So let's look at the smart network. I did a dictionary search of this word, smart network, and this is what I got. So this doesn't exist. There ain't something that has been recognized by this industry that they can put a name on and call it a smart network. Any reasons why that's the case? 14 years of smartphones, no smart network yet.
We've got dumb points.
Okay, they're not smart, they're dumb. Anything else you can think of? No apps, okay. So it's not programmable, exactly to your point, right? Nobody can build apps for it. It's built by domain experts for domain experts, right? Only experts understand this. Now, the reason for that is, obviously, the network has to do all the work, has to connect to multiple smartphones. But underlying all of this is an element of complexity that we need to understand and appreciate. So that's what this panel is all about, understanding that complexity and dumbing down that complexity to a point where you can provide platforms, provide APIs where anybody can build apps for a network and thereby build a smart network. That's the journey we're on, and that journey is going to start here today, right now. And that's all, and we're all part of it, right? So we're going to address this question of optimization and automation of complexity and how we're going to address this and end up with a smart network, hopefully soon. So this session today is made up of 4 parts. First, we're going to have a panel on managing complexity, working through approaches and solutions, asking the question, what is complexity? How do you define it? How do you measure it? How do you optimize for it? So we need to first understand that and make sure everybody is able to appreciate the nature of this complexity. Once we've gone past that, in all the panels today, we talked about Open RAN needing an ecosystem. You need an ecosystem of developers, ecosystem of testers, ecosystem of products coming together to make Open RAN possible. So we're going to talk about how do we apply that to RAN optimization, how do we rally together a community of developers to address this. And then thirdly, the third panel will address the journey that we've taken so far. There has been solutions out there in the name of self-organizing networks. They came in with a lot of promises. Some of those promises have been fulfilled. A lot of them have not, depending on who you ask. So we're going to follow that journey. We have a set of panelists who are industry experts, operators and vendors. So they're going to tell us the journey that they've taken and where we've at what point of that journey we've reached so far and where we're going next. Finally, given that we've had some delays today, we were planning to do a demo here for this audience. I don't think we're going to be able to get to it, but fear not. There are demos in the demo area. So look out for a RIC demo in the meta area. Look out for a demo from HCL in the HCL demo area. They're going to be demonstrating a traffic steering use case running live on a OSC RIC, which is the ORAN Software Community RIC, and apps developed by HCL. So these are proof points that the technology is there, proof points that ecosystems can be built, proof points that there are vendors who are taking advantage of what's already there. I have a partner in crime today with me, Stefan Thoralf. He's one of my favorite analysts from Light Counting. So I'm going to moderate session 1 and then pass on the mic to Stefan for the next 2 sessions. Okay? So I'm going to invite the panelists for session 1 to the stage. Heiko Lehmann from Deutsche Telekom. Olivier Simon from Orange. Madhukiran Medithe from Rakuten. So those are our 3 operator panelists. Thoralf Czichy from Nokia. And last but not least, Sheriff Sedki from VMware.
Still free.
Yep. So we talked about the RIC a lot. I'm going to give the panelists a minute to introduce themselves, but I'm going to ramble along a bit more here, just to set some more context. We talked about the RIC a lot. I'm sure a lot of you know about this technology that Open RAN has introduced, but this graphic is something that clarifies what the RIC platform is. There's a near-real-time RIC and a non-real-time RIC. A non-real-time RIC covers a wider area, does more holistic optimization across a network, which could be a metropolitan area, a large area, consisting of dense urban sites that needs to be optimized. Then you have the near real-time RIC that addresses a particular smaller cluster addressing a certain set of problems that could be seen that's unique to an urban area versus problems that may be unique to a rural area and so on. There are specific interfaces that ORAN Alliance has defined that the RICs use in order to collect data, in order to close the loop and optimize those platforms. So this is just to set context so everybody knows what a RIC is. That acronym has been thrown around a lot today, just setting some context for it. Next, we're going to talk about complexity. Clearly, there's a need for driving intelligence and automation in radio access networks, right? That need's well understood. And this is required so we can help MNOs address constraints and complexities in RAN operations. So before our panelists start talking about complexity, it might be good to talk about what are these different types of complexity that we deal with. There's one category of complexity I'd call inherent complexity, which deals with spectrum, the fact that you have interference, you have fading, you place radio units in different places, you have to manage energy and so on. Then there is something else called induced complexity. That's just a fact of life, right? Operators have to deal with multiple technologies at the same time, have to allocate these technologies to different spectrum, deal with mobility, traffic patterns, and so on. So there's these different types of complexity that you have to understand. Today we're going to talk about the dynamic aspects of complexity, not so much the static aspects of complexity, and see how we can manage them, right? And in order to address this, we need these platforms like the RIC. We also need to solve problems by bringing together software players from different organizations to understand the natures of these complexities, understand the nature of the applications that we need to solve, and then provide specific solutions for solving those problems. So that's kind of the background. I'll let the panelists introduce themselves real briefly because we've got a lot, stuff to cover still. So we'll start with Heiko from my extreme left
Yes,
here.
good afternoon. Hi, I'm Heiko from Deutsche Telekom. I must apologize for this longish title there. That's corporate folklore as you know it. Yeah, so I'm just from Group Technology in Deutsche Telekom from T-Labs.
Yeah, so Olivier Simon, Orange, with a long radio access network background and now focused on data and AI. Oh, not working? Okay.
Hello everyone, I'm Madhu, working for Rakuten Mobile, heading data science in Rakuten Mobile. Yeah.
Hello, my name is Thoralf Czichy. I'm heading the RIC platform architecture at Nokia, and I'm also working as a project technical lead of the Open Run SC software community near real-time RIC project.
Hello everyone, my name is Sharif Sadian, Telco Cloud RAN specialist from VMware, looking after VMware RAN products and mainly RIC.
So thanks, panelists. Clearly, you understand this complexity very well, representing operators and vendors. I'm going to start with a question for each of you. It's kind of a two-part question. What are some, pick any area of complexity that we talked about so far, and talk about the impacts of that complexity, and what are the constraints that it imposes on your ability to operate your network. So again, we'll start with Heiko.
Yeah. If I may, Murali, I would like to come back to the term complex systems for just a very short time, because sometimes when managers talk about it, it's just an alternative word for very complicated, which is not true. Yeah? Complex systems have a certain hallmark to them, and that is that it's a large system made out of a multitude of components, and these components have local interactions, binary interactions with one another. And out of this kind of local and reduced interactions, there are then emergent global properties. And this is the real property of complex systems. You can think about the climate system, yeah? And you can think about a tree, and there's photosynthesis, interactions with light, there's the roots interacting with the soil, and so forth. And in disaggregate telecommunication networks, we have the same properties. Yeah? We have broken down the integrated thing into little bits and pieces, and then we have hardware components, software components, we have supply chains. Actually, it's a network. Yeah, chain is a linear picture, which is not true. Yeah, it's a supply network, and then you must watch out for these new global properties. And for instance, we have the same. As you have been asking, I should give an example in the network management. In the RIC, which is our topic here, we have a breakdown of things to manage into individual use cases, and then we have apps attributed to each of the use cases, and then they reside side by side, and you think the world is fine. Every app manages what it's supposed to manage. But then you realize there's overlap in the action space and different cost functions. Yeah? So an energy-saving app would like to bundle traffic in certain places in order to switch off others, whereas classical load balancing traffic steering would aim for an equidistribution. And that's a conflict, and it's happening in the same action space. And this is the kind of emergent property which I would like to address, and actually we're doing that in the Telecom Innovation Labs and a number of projects. I have been talking too long, sorry.
Olivier?
So I will try to make a shorter...
Sorry.
So I think there is a big source of complexity that was actually not on the slide. It is that the radio access network is big. I mean, the largest operator in the world have more than 1 million of base stations. Tier 1 operator have typically somewhere between 100,000 base stations to let's say 500,000 of base stations. So it's a first source of complexity. Another source is that we are multi-technology. We have 2G, 3G, 4G, 5G. And 5G as such is a big source of additional complexity. We have introduced new technologies such as beamforming, such as network slicing, that create really different kind of complexity. And just to finish on Open RAN, what is interesting with Open RAN is, okay, we have the multi-vendor aspect, which could be a source of complexity, but if you're thinking about it, actually it's not really some new complexity. It's some kind of transfer of complexity that was previously visible for the large RAD vendor, the Nokia, the Ericsson, Samsung, and so on. They add this complexity to manage. And as an operator, we say, oh, it's more complex. But actually, it's a transfer of complexity from the RAN vendor to either the system integrator or the operator. And we have that to manage, by the way, together with the RAN vendors.
Thanks, Olivier. Madhu,
Right,
try to
so-
keep these answers short because I know we have a lot of
Right, I mean,
material to
mostly
cover here.
Heiko and Oli already covered it.
Sure.
So yeah, let me explain with respect to vendor side. So the main significant impact, what I see is the monolithic vendor has to break down their EMS system. So which is very big task from the vendor perspective, and it's very complex. Because when we go with Open RAN, which offers us to choose the particular vendors, and they have to come up with the common OSS system. So the key players in the RAN segment, so they have to come out from their proprietary interfaces from the management side, and they have to align with the requirements of the operator and the openness. So that's one of the key complex what I see from the vendor perspective. And also the size of the software, basically the modules. So when you're going with the cloud kind of environment, as a microservice-based architecture, definitely they have to bring down, scale down their particular image, so that the functions the modules will work in more effective way. So these are the two basic things where I see the vendor actually more struggling over there. So of course there are some points when we have OBF kind of framework, where you will get all real-time statistics and KPIs, where you can develop on your own models, AML methods. So definitely that is one way which we are actually following today in the industry.
Thanks, Madhu. Thoralf?
Yeah. So when Heiko mentioned this complexity arising from interacting entities, and I think when you think about the run where we do have G node B, the algorithms within the G node B already very complex, and then we make it even more complex by having G node Bs talk to other G node Bs over XN, or then an E node B over X2. Then we now add the near real-time RIC as one more entity that implements a particular algorithm, and then on top of this we have the non-real-time RIC or the SON solutions. And I think all four of them actually need to work together, and you need to have clear responsibilities and limits on what each layer, if you assume a layered approach, is responsible for, and where are the limits of each layer, and then you hope that eventually the complexity of the overall system actually reduces as long as you introduce limits and responsibilities carefully in each layer.
Very good. Thank you, Thoralf.
I see one of the complexities, and it's more close to my heart, about we're having multiple technologies and multiple frequencies, and spectrum is the most expensive intangible asset. And we are little bit inefficient using it. And now we have carrier aggregation challenge. We have now non-standalone, where which anchor layer from the LTE, which is like, and all this layering strategy and challenges, most of the time is manually or with templates, which is not fitting the real traffic needs and predictive needs if we can implement some machine learning algorithm. And what I'm expecting is that we are wasting part of this value, and we need some more automation to solve it.
Sounds good. So let's assume that complexity has been explained, and all of us understand what complexity is. Clearly, we could be talking about it for another day, but let's assume that we got past that and we have a family of app developers out there building apps. So I'm going to ask a question starting with Olivier. How do you deal with conflicts between apps? And I'm going to follow up that with you, Heiko, on the SLAs of these apps. So think about that. Each app developer is going to say, I'm going to guarantee X. Obviously, all the operators out there are buying these apps to improve something in their network. So the guarantees are going to come from each of these vendors. So how can we, when we have lots of different apps and sometimes may conflict with each other, how can we guarantee that SLAs are met for each individual app? So how do you manage conflicts? How do you enforce SLAs? So those are two questions for the two of you to think about, but let me start with Olivier.
Okay. Currently, we are managing conflicts really basically. So we avoid conflicts. You know, it's a bit like interference. With 2G, we are avoiding interference. With 3G, we are mitigating interference. With 4G, we are kind of coordinating interference. And with 5G, we are taking advantage of interference. And with conflicts, we are at the first generation. We are avoiding kind of statically the conflict. So we select, to some extent, the apps in a way that they should not act too much on the same parameters, or they should not create indirect conflict with parameters. With time, we will progressively make the same thing as interference. We will first mitigate it, we will coordinate it, and finally, maybe we will taking advantage of different apps working on the same parameter to have the best result at the end with the help of AI, of course.
Sounds good.
Yeah,
Heiko.
I start by answering the question put to Olivier, and beg your forgiveness. What do we do about conflicts? We have 3 steps. The first is to detect them, really. Second is to give a measure to them, how severe are they, and then only then we can start to mitigate. Yeah? And for that, we need a sensible simulation system. We call that digital twin. This is the trend word for it, and it's difficult to do because you have to put things in scope and put things out of scope, which is a difficult decision to make, and then build the system. But when we have it, we can give a measure to it, and we can understand it. And then we can worry about SLAs. You said we have understood complexity, which is fine, yeah? And then we will have understood that there's different dimensions. And there is the technical dimension in understanding the interaction of the apps in the action space of the system. But then there's the techno-economical dimension. And this is where the world of SLAs belongs to. And then, of course, it's a management question how to deal with that. But first, we need to understand the interaction. So I do not have a solution for decoupled SLAs and finding overarching ones. But at first, I need to understand the technical side of it.
Thoralf, you have a follow-up to that?
Yeah, maybe I can jump in. I think there was, at the end, Olivier mentioned machine learning as a solution. And I think that's clearly the path forward. I don't think actually Working Group 3 they have 2 pages in the specification of the RIC, near real-time RIC, about conflict detection and mitigation. And I actually think the approach is wrong. What we should ask ourselves instead is, given a particular problem, which kind of X apps can I combine in a way and configure so that they solve the problem the best way? Always considering the cost function and which KPIs you optimize for. And I think this is how we should address the problem, not via conflict detection, where then immediately when you have detected them, you ask yourself the question, how do I mitigate them? And that's the complex problem actually to solve, not the one about conflict detection.
So Thoralf, thanks for chiming in. But I'm going to ask you a follow-up. I know we're kind of short on time, but maybe a short answer from you. I'm sure a lot of folks in the audience are wondering, introduce AI ML, it probably comes with security risks, right? Malicious data could be misleading the models to do malicious things potentially. So I want to ask you first about how we detect any type of maliciousness in building models, right? And how do you bring in security there? And I want to follow up with Madhu and ask him the lack of determinism, because when you ran SON and other solutions in the past, you knew exactly, and so I think some of you mentioned that you knew at a certain point in time you did X, a certain other point in time you did Y. With AI/ML, a lot of things are predictive, and you lose that determinism. So I want the last 2 questions to you, Thoralf and Madhu. Security and lack of determinism, how do we address that? And then I think we're going to close the panel, and I'm going to pass on the mic to Stefan, as I promised.
Yeah. I think if you think about the security of machine learning algorithms, and then you mentioned deterministic behavior. I think what we're actually looking in machine learning algorithms is explainability. And there's a research branch under ML which is about explainability of AI models. And you need this for security reasons. So in order to be able to say whether that algorithm is doing the right thing or not. And then you also need it for ethical reason in order to be able to explain. And then on the security angle, I think that's actually what we should research more. There are algorithms like Lime or Retain that add explainability to existing models. And if we solve that problem, I think then we can start talking about security of ML models. Maybe as a reminder also, in terms of attack surface, machine learning models are actually very similar to what apps are in these app stores by Apple and Google. They have the same problem. They need to scan apps for maliciousness. And the attack surface is huge. They are also using machine learning to figure out whether there is actually malicious intent in one of those in one of those apps in the App Store. I think we need to do something similar for the machine learning models that we use in the near real-time RIC and in other places in the run.
Yeah. So with respect to the determinism, sorry. So yeah, it's a good question. Basically, how you can see the standalone, the rule-based mechanism versus the probabilistic machine learning. Yes, of course, when you go with the rule-based mechanism or statistical model, job would be done 100%. But when coming to the machine learning based mechanism, is a probability function of efficiency of 70 to 80%, what we see the accuracy perspective. But coming to the Open RAN, especially on the RAN segment, RAN is very dynamic. So the configurations, definitely we will not apply across the holistic to the network. So it's the rule-based definitely will not work, because we need to understand what is the pattern of the particular cell, what is the nature of the particular cell, what are the applications, at what time people are using, the traffic conditions. That model has to be trained. That has to come across your time series models or neural networks. Basically, that will tell about how my network is, what are the applications users are using. Because we're already talking about bringing edge to the close to the subscribers, meaning to the RAN segment perspective. So in that conditions, definitely AML will play a crucial role. I will give one example, like the carrier aggregation, which we're talking about millimeter wave, where we have one of our colleagues, we have mentioned about the carrier aggregation perspective. In millimeter wave, we have abundant of band up to 400 megahertz, which we can do that. So if you go with the statistical model, where you can enable carrier aggregation across all the cells, it doesn't need to go with the efficiency perspective. None of the users or none of the devices are capable under that particular camping of cell. So where your ML model will actually see that, what type of devices are there. So should I see enabling of multiple bands of CA or not, based on the traffic pattern, based on the congestion of the network. So that leads to the efficiency of the energy perspective, and also it will improve the efficiency of the network perspective and leads to the spectrum efficiency and user experience. That's a trade-off basically when you go with the.
Good.
Yeah.
Thank you, Madhu. I want to thank all the panelists for joining us to tame complexity. I'm going to pass on the mic to Stefan now, who's going to bring our next set of panelists onto the stage to talk about how can we build apps through an ecosystem of developers. So thank you all. Applause for the.
Thank you.
Thank you.